Hello everyone and welcome back. In this video we're going to cover kind of one of my more popular shorts that I posted, and we're going to show you how to encipher and decipher a message. And this is kind of going to act as your part one, almost, so to speak, like challenge or kind of big project you can show off to someone that hey, I'm learning Python and here's something really cool I built out with it. Now before we dive into the whole thing, we'll get started with some simple stuff and then explain what we're going to do along the way. So first, we are going to have to do one import, and so we're going to say from random import rand int. And let's just first again explain kind of what imports are. We haven't dived in fully to what they are, but we can just give a little filler here for about a minute. Essentially, when you install Python, you don't just get Python, but you get some custom written codes, functions, files that people have thought were so important that the people who created Python said, why don't we just include that in what we call the standard library? But we don't want the person using Python to import all of those extra functionalities every time they want to run a file, because that would be really expensive on memory and kind of computer hardware. So we're not going to essentially give them access to it unless they specifically ask for it in order to conserve their memory. Now that's essentially what imports are. So you have the random module, we would call it, imported into your Python library, but you don't have access to it unless you specifically say, I want to use something from the random module, and specifically I want to use the random int. And again, we'll go into imports in a later video, but for now, just know that that's what we're doing there. You already have it installed. You just need to write this line of code to be able to have access to this functionality. Now, from there, what are we going to be doing? We're going to be enciphering and deciphering a message, and the best way to learn about that is to first learn about the basic Caesar cipher. So give me a minute while I go ahead and write out all the letters of the alphabet and the numbers 0 through 9, and I'll pause the video and let you know when I'm done. All right, I'm done. So I've now written all the letters of the alphabet in order and the numbers 0 through 9. Now the last thing here is to make a dictionary comprehension, and we learned about how to do that in, I think, my last video. And so for every character index for index character in enumerate alpha num. All right, so what's going on here is that essentially we need a way to encode and decode messages, and let's look at, well, just what this cipher is for right now. What this cipher is it's essentially a dictionary saying, hey, A was the first index of the alphabet, B is the second letter or first index of the alphabet, so on and so forth. So it's just a way of saying, hey, for every letter in the alphabet, we now have a numeric code of accessing it, and also the numbers 0 through 9, but because of the order they come in, they're now associated with different values. Now this is essentially our key and how we encode or decode a message. And let's look at what we would call the basic Caesar cipher. So the Caesar cipher was one of the first ways that people started encoding messages. And so what you would do is you would have some sort of message, and you would say for every character in that message, right, you would then want to maybe print out the cipher, or in other words, the numeric code of that letter for each letter. All right, so let's define that function, and then we'll even write the Caesar cipher of I like Python, because we haven't yet written in how to deal with spaces. All right, so there's I like Python, but now based on every index value of every letter in this code. Now what you would then do for a Caesar cipher is you would then maybe say, why don't I add some unspecified or secret amount? And that was the whole key, was what amount are you adding? Let me add some amount to every one of those characters. Now when I run it, well, all the characters are just a little bit different. But the final step is to say, what if instead of writing all this as numbers, what if I then take all these numbers and then put them back into the alphabet, so to speak, or back into the characters I'm allowed to use by then using that new index value as the new letter I'm going to use. So I now say I want alpha num at the index of whatever the old index of the actual letter I cared about was, plus this filler amount. Cool. Now I've got a secret message, right? I like Python. Now it looks like a bunch of garbage letters. Now, there is one issue with this right now, and that's that if I wanted to add 20 to every character, well, take a look at where T is in the code, and think about what's going to happen here if I run this right now. I'm going to get an index error. And why do we get an index error? I think we get it before T, but we'll still see why. It's because, well, for T, for instance, T is already right here. And if I were to add 20 values to this and then try to get the value at the index 20 above where T already was, well, I'm out of range, and that's what we get, right? I'm outside of the amount of characters that were actually in my alpha num string. So this is now broken. And there's actually a quick fix you can do here, and it's all thanks to the modulo operator. I can mod this by the length of how many characters are in alpha num, and now that all works fine. Because essentially, if you now go past the amount of characters, it's going to loop back to the beginning. That's what this mod alpha num is going to do. Be careful that the mod alpha num is after a set of parentheses wrapped around everything. Now, let's just show you that this works by maybe going back to like adding 4 and putting 8 at the end and explaining what's going to happen. So for the character 8, if we add 4, it's going to add 1. It's going to add 2, but instead of breaking, it's going to mod and go back to the beginning. And then add 3 and add 4. So instead of seeing 8 at the end, we should now see C at the end if we've written this correctly. And there it is. Okay, we're almost done. Instead of one character at a time, why don't instead we then say coded message. We'll start it off as an empty string. And then what we'll do is instead of printing every character, what we can do is we can take our coded message, and we can append every new character we get. And we can finally return our coded message. So now there's the same text, but instead of being printed out one character at a time, it's now printed out every single letter at a time. Now, how would you decode this? Well, great question. You would simply just undo everything that you just did. So we'll call this Caesar cipher undo. We would have a decoded message that I want to find. And then for every character in my message that I got, the decoded message would then be minus 4 length alpha num and return my decoded message. So in other words, we're just undoing the addition of that certain like mystery amount. We just undo it and then still put it back through all the same code, right? Get the character I had, undo the amount I added to it, make sure I cut that off by the mod to undo the overflow I maybe had, and then, hey, now it's that new character, and add that to my decoded message. All right, so let's see here. Now what I can do is I can say my, coded message is equal to what I get out of my Caesar cipher, and I can print that coded message really quick. And then I can say my decoded message is equal to my Caesar cipher undo of my coded message. And then, of course, I can print my decoded message. And there we go. So now we're encoding I like Python 8, and we're undoing I like Python 8, but we're not at Python 8, we're at Python 3.12. So there we go. Now, again, what you can do is you can change this, and you could say you want to add 17, and you want to undo the adding of 17. The key here is that the real secret to this message is just whether you add 17 or subtract 17 or add 8 or subtract 8. It's all about that one number there that's the entire thing that's holding your entire code in place, essentially. So what I wanted to do was I wanted to say, well, let's beef up the basic Caesar cipher and make it feel a little more complex, but it's ultimately still just as simple. Now, what I'm going to do is I'm going to draw out something here in code, and I'm going to show you what I would do. So let's say I just had the string Python, right? How would I beef this up? Well, I think what I would do is I would add a certain amount of filler characters. So maybe 4 characters for every actual character I care about in my string. Right? So there's 6 like spaces, so to speak, for every 6 letters in Python. And what I want to do is maybe I want to just say, not only am I going to fill in some undetermined amount of filler characters, maybe it's 4 characters per actual character, maybe it's 7 characters per actual character, maybe it's 40 characters per actual character. Well, based on those 4, 7, or 30 characters, which one's the actual one? Maybe it's the second letter that's the actual character in the string that I originally had. All right, so maybe the second character out of every 4 is the real character that I care about. Now, not only am I going to add in a bunch of random filler, not only am I going to care about only a certain character for every like second value in my list of fillers, but also I'm going to apply my basic Caesar cipher to each one of those second characters in this example. So that's what we're going to code out, is a way to say we have an undetermined amount of fillers. We don't know which character is the actual one, but we'll determine that. And we'll still apply the Caesar cipher to that specified place in the actual fillers. So we'll still apply the Caesar cipher to every second character in my junk 4 characters. And that will be where my coded message actually is. So it ultimately is the Caesar cipher, but it's going to feel a lot more complex, and it's going to test your knowledge of a lot of Python concepts. Oh, and there's one more really cool thing, and that's that what we're going to do is we're going to change up per word, right? So maybe this word, I want 6 characters to be junk, or like 6 characters to be filler, but only the 5th in the is the actual character that I care about. So that's something else we're going to do. We're going to make every single word have its own like kind of encoded way of being encoded. So for Python, it's every 4th, every letter is now blown up by 4 characters. Only the second character out of every 4 is the actual letter. And that second character is going to have some amount added to it, like a basic Caesar cipher. But for is, it's going to be a different method. Now, how are we going to make sure we can decode every single word, since every word has its own method? Well, that's what we're going to do, is we're going to essentially put 3 characters in front. And those 3 characters are going to be the amount of filler. So every 4 characters. We're then going to put in the actual value we care about, aka every second character. And we're also going to put in the movement amount. In other words, the Caesar cipher amount. So every word is going to have 3 special characters out front, and they're going to be the key to decoding every single word. So every word is unique. Every word has its own fillers and the actual character we care about. And also it's going to randomize every time we run this code. So that sounds like a lot. It's going to be pretty simple, and it's going to happen in under 40 lines of code to encode and decode all together. So let's go ahead and dive in. So we're going to adjust the Caesar cipher, and I'm just going to call this my cipher, and we'll even just get rid of this for now. So let's just talk about ciphering this craziness. And I feel like I just need to clear my outputs and restart my kernel for a second, just to get rid of the other stuff I've already done. So, okay, I've only got this so far, and I'm making out my new cipher. So maybe I'll even call this encode, because I'm going to encode a message and then we'll decode a message. Okay, so the first thing I'm going to do is I'm going to, start off with a blank coded message, just like before. But now, instead of just going through every character, I think I want to be able to handle like words, like I was talking about. Like Python is cool. Those are 4 words. Let's find a way to deal with every word one at a time. All right, so I'm going to hold on to this, because that's going to be a pretty important key, because it's still basically how we're running through things. But okay, what am I going to do? So I'm going to say for word in message.split. Now, if you haven't used message.split or string.split, let's show you that. In fact, let's even write Python is cool, and then let's write .split. And you can see what .split does is it splits every white space character. It will essentially say, okay, that white space must mean like the end of a word and the start of a new word. So it breaks every word or every list of characters separated by white space into their own little sections and puts them in a string. So now I've got every individual word, which is kind of what I was saying up here I wanted to do. So for word in message.split, because now I have every individual string or word as a string inside of this list. So for every individual string inside of my list of strings now, what do I want to do? Well, again, I've got some amount of filler, so I've got some amount of extra characters. And this is where we're going to use randint. Maybe I want 2 characters, and maybe I want up to 30 random characters per actual letter. All right, so how many fillers do I want? Do I want 2 extras, or do I want 30 extras, leaving me with 31 letters per character in a word. All right. Now, then the question is, what's the actual character that I care about? Well, it's going to be another rand int. It's going to change per word, and it could be the first letter of every like sequence of 4 or whatever characters, and it could be up to, well, the length of how many characters there are in my alphabet, because we don't want to go over, because otherwise we're just going to run out. So that is one key to writing this, is that we need to make sure this amount and this amount are less than the actual amount of characters. Otherwise, things will get messy and we won't be able to get back to our decoded message. All right, from there, how much are we going to move every letter? Now, this is the actual Caesar cipher. Like, do we want to add 4 to every index? Do we want to add 17 to every index? What do we want to do per index? And, well, once again, we're going to randomize that per word. Now, we need to add at least 1 so that it doesn't remain the same, but we also need to have it be less than the amount of characters in alpha num as well. Oops, sorry, this shouldn't be that. This should be up to extras. My bad. So it could be the first amount in the amount of total characters. It could be up to the amount of the last value in my extras. Sorry, one little clarification there. Okay, but the movement, again, I need to move at least 1 character, but I don't want to move all the way up to how many characters there were, because otherwise I'd get back to the original letter after I go through all the overflow. I could end up all the way back at the beginning. So move at least 1, but move up to 1 less than the amount that there are. Okay, now what are we going to do here? Well, now we need to start adding stuff to our coded message. So what we're going to add first to our coded message is those 3 characters per word. So we're going to say I need the alpha num of the amount of extras that I want, plus the alpha num of the actual character that I care about, plus the alpha num of the movement amount. So in other words, again, every 3 letters of every encoded word, or every 3 like characters that still get jumbled up and mashed around, are actually the way to decipher every single individual word. So the first 3 are the special values that will decode your message. Now, from there, after the first 3, we actually have to start placing in the fillers and caring about which one's the actual and all that stuff. So let's do this. So for character in word, all right, what we're going to do is we're going to then say for x in range extras plus 1. And what we're going to say is that I want a new character. Oops, sorry. I want to say if x is equal to the actual value. Now, in other words, what are we handling here? We're saying, I know there's going to be a bunch of filler letters, but if I'm at that filler letter, if I'm at the second of every 4 characters, so to speak, if I'm there at the actual letter I care about, then I need to specifically encode this somehow, and that's where I'm going to actually borrow this code from before. I'm going to specifically say my coded message needs to be my cipher applied to my character. Also, we're going to put character.lower because we're going to want to handle uppercase as well. And instead of adding specifically 17, we're going to make that based on the movement value. Okay, so again, what we're now handling is if I'm at the specific character, the second character of every 4, so to speak, then I need to make sure I specifically move that character's index by a particular amount and handle overflow, and that will go into my coded message. Now, what if I'm not at the specific character I care about? Well, then I just need to throw in garbage letters. So I can actually just take my coded message and I can add the alpha num of any random integer from 0 to 35. In other words, just give me any junk character. Well, not 35, but the length of alpha num, because maybe we want to add in punctuation later on. Let's make our code flexible. Great. So at that point, what are we going to do? Well, after we've encoded every word, we should put back in the space. So we'll take our coded message and we'll add in a blank space. Now that's going to do one thing for our return statement. That means there's going to be a blank space at the end of the last word. So let's just go ahead and throw that off by saying, give me everything in my coded string now, except for the last character. In other words, except for the last space I added to the last word. Okay. Whew. that was a lot. But take a minute, pause, look at all this code and reread through it, and let's see this code in action. So I now have a coded message. I'm going to write encode instead, and I'm going to actually put my spaces in there. And I'll say I like Python 3.12 because that's the one I'm working out of right now. And we'll print our coded message. All right. Oh, and I get an index error. Let's see here. String index out of range. Rand int length alpha num. I think I need to do length alpha num minus 1. Let's try that. Great. Okay. So now, yeah, because I forgot that rand int will actually go up to the last value, which would overflow if we typed in length alpha num. So rand int will include that max value, whereas like usually range or something like that excludes that last value, and that caught me right there in that moment. Okay, but what I hope you notice is that now I've taken I like Python 3.12 and I've gotten a complete garbage absolute mess. Now, also what I love about this code, again, I think it's so cool, is that the simple single letter I actually has all of these garbage characters. So you might think this is a longer word than just the simple I. And if I run this again, we get wildly different results. But the idea is this will still be able to be decoded correctly every single time, because the first 3 characters, right, the first 3 are the actual key to decoding the message. The first 3 characters are the secret numbers, but they're encoded as letters, of how many filler characters there are per real letter I care about, the actual value of where I'm going to undo the Caesar cipher or do the Caesar cipher, and how much the Caesar cipher moved every single letter. It's all baked into the first 3 letters of my encoded message. So that's pretty darn cool. Well, we've encoded this message, but now the question is, how do we decode it? And I would actually recommend that you pause this video and take that as a challenge to yourself to see if you could decode this, because it's almost going to be the same logic, just undone, like the basic Caesar cipher was. So hopefully you took a chance to try that out, and let's make a decode for my message. Okay, so it's going to start off in a very similar way. The first thing we're going to do is we're going to take our decoded message, and we're going to start that off as an empty string. And then we're going to do a similar process of saying for word in message.split. So starting off pretty similar. And now, right, instead of choosing random letters or random movements or actual characters or how much we're moving by, we now need to not get a random value, but decode that random value. And that's why, right, we made our cipher in the beginning to essentially undo the encoding or get back to the index of what we were at. So what we're going to do is we're going to say, all right, the extras per letter are going to be the cipher amount of the first character of the word, which is at index 0. Now from there, the actual character I care about per word is just the cipher at the first index, because it was the second thing we typed in. All right. And last but not least, how much did we Caesar cipher essentially every word? How much did we movement every word? Well, that would be at the third character or the second index per word. All right, so great. We now have captured all those movement amounts. And now what we're going to do is we're going to say for character in every single word from the third index on, because again, the first 3 were those characters or those special decoded values. So after those special values, now we're into the meat of the actual word. And we need to essentially process junk characters or non-junk characters. And so that means if I want to decode the second character or first index of every set of garbage letters, then I need to start counting how many garbage letters I've seen. So before I dive into this for loop, I'll set my count equal to 0. How many letters have I seen so far? Well, 0. And let's see here. If this count, right, happens to be at the actual letter that I want to decode, well, then what I need to do is I need to update my decoded message, and that's going to be plus equal to alpha num at my cipher at the character, and then let's see here, what's it going to be, minus the amount of movement, and finally mod the length of alpha num. All right, so what's going on in this big ugly line right here? Well, again, what this is saying is if I'm at the character I care about, right? If the count, if I'm at like the first index, and the first index is the actual value I want per like group of garbage characters, then what I want to do is I want to figure out what index that special character is specifically at, undo the amount I Caesar ciphered it, and then mod to undo maybe any overflow. So that, in other words, if I got to D by being equal to 8 before, then when I subtract, I need to then redo the mod to get back to 8. So I need to account for the overflow by modding, and I need to account for, I guess, the underflow for going backwards by still modding at the end there. All right. Now, what if I'm not at the actual letter I care about? Well, then maybe I'm before the letter I care about or after the letter I care about, but either way, I'm going to need to plus equals 1 my count. The last question is, what if I've made it to the end of my word, because, or like the end of the first 4 sequences of characters? How do I handle that? Well, if my count is equal to the amount of extra characters I threw in plus 1, because there is one real character, then restart my count at 0. And at that point, I can then take my decoded message, I can add a blank space, and I can once again then return my decoded message, except for the last garbage space that I threw in. All right, finally, wow, that was a lot. But let's see here. I now have a decoded message, and that's going to be equal to my decode of my coded message. All right, and let's run this and hope we didn't get any errors. Whoops, I need to print that out. Print decoded message. And I think we've now done it. So we can see, we've done something here. Mod length alpha num, mod length alpha num. Give me a minute here to figure out what happened. Got it, figured it out. So even if I am at the actual character I care about, at the end I still need to plus equals 1, regardless of whether I'm at the actual character I want or not. And there we go, let's see it now. There we go. So now, again, you can see that I'm encoding and decoding that message every single time. And even though the encoded message looks like absolute wildness, it's always decoded correctly to I like Python 3.12. It can also handle uppercase and lowercase. So I can say, I love learning Python. And you can see that it'll still just lowercase everything. It won't go back to uppercase, but at least the uppercase letters didn't get in the way of my code. So I hope you found this project really kind of insightful and fun. It's really tricky. Hopefully you follow the logic of what's going on here. But every time I run it, it's super fun to me to see that message just change what it is every time, but still decode correctly. Now, the very last thing to maybe say here is, should you use this to encrypt or decrypt your messages or keep your files safe or anything like that? And I think the short answer is no. You should not use this code. Even though it looks fairly sophisticated, I wouldn't use it to encode or decode anything like at the production level of whatever company you're working at, because ultimately this is a basic Caesar cipher, and it's like the first thing anyone learning cryptography learns how to encode or decode is the basic Caesar cipher. But I think the one question is there something that makes this actually special and unique, and what is like the key to encoding or decoding this? And the answer, if you think about it, is the letter or the order you consider the letters of your alphabet. Because if I know the order of the letters of my alphabet, this is actually fairly easy to encode or decode, and any Caesar cipher is. However, there is one thing you could do to actually beef up the security of this, but you'd have to keep it super secure. And to do it, we'll have to import something else from random. We'll have to say from random import shuffle. This will take a little bit, but here's what we're going to do. We're going to say that I want the alpha num list, and that's going to be equal to, let's do this, x for x in alpha num. And then I'm going to want to do alpha num dot, not dot, but I'm going to want to wrap shuffle around alpha num. Now the reason I had to turn it into a list is if you look at the documentation for shuffle, it says it needs to have a mutable sequence, aka not a string, so a list or a dictionary, and it will shuffle in place and return none. So just writing shuffle right here is already going to shuffle my alpha num list. And then what I could do is I could then say I want to print, and here's another string method. It's kind of the opposite of split. I can do blank dot join alpha num list. All right, now when I run this and I print this out, shuffle alpha num list. Might have to rerun this and rerun this. There we go. Now this right here, I've just shuffled these basic letters of the alphabet. Now if you actually put that into your code here at the beginning and you keep this top secret, now you've actually created something, I would say, that's fairly encoded. Because if you are just assuming that the letters of the alphabet in your numbers 0 through 9 are going in order, then you really don't have that much to undo to figure out what the actual message is. Because if you knew the letters in order of the alphabet, these first 3 characters are once again giving away, right, in some way, the numeric codes of how you shifted everything exactly how, and it's the first 3 characters. So like if you can keep this code secret, that the first 3 characters are the dead giveaway of enciphering or deciphering, and if you can keep secret the order of how you're considering the alphabet to start and end from with your numeric characters, then now you actually do have something that is pretty darn encoded, and it would be very difficult for someone to figure out. But again, it would be probably really easy for someone to figure out, oh, the first 3 letters are actually the way this is encoded or decoded, and oh, their alphabet was going in standard order. But if you can keep those few things a secret, then this is actually a pretty darn clever way to encode or decode. Again, I'm just once again saying, please don't use this in production level code, because I am not a PhD in cryptography by any means. But I really hope you found this project cool. You got to revisit a lot of topics we've discussed, like basic string methods, basic list methods, understanding modulos and divisions, understanding string methods like lower and split and things like that. It all came into play here with 2, I would almost argue saying basic functions, but it took a lot of discussion to understand what's going on, especially if you don't have kind of a higher math background. And that's okay. That's what we're here to do. We're here to learn. So I hope you have a lot of fun with this. I hope you share some secret messages with your friends. And I hope to see you in another video where we probably really soon will be able to talk about Python classes and really step up our knowledge. But we'll have more projects, probably functional based along the way. Thank you so much for watching, and I'll see you then.